Okay, let's get started. So yesterday we looked at finding the circumference of a piece, which we called an arc. Today, for just a short time, we're going to look at the area of a sector, which is just a piece of the circle. And then we're going to move on to the next topic. And as you guys know, I cleaned off my desk during your TBA, and it is already a hot mess all over again. And what's it been? A day and a half?
Why do you have 3 cups?
We've had lemonade for Teacher Appreciation Day yesterday, and they gave us lemon cupcakes. And it was really good. So yesterday I went back and got a second thing of lemonade. And then today they still had a little bit left over, so I got a third. And I just don't want to throw it away because it reminds me of how good the lemonade was, but I need to throw it away just because, it's too much of a mess. All right, so if you would turn to page 4, we're going to do 1 or 2 problems on page 4, and then we're moving on. Because I feel like kind of what we're working on, we've already looked at in the circles unit. So page 4, number 4 says, find the area of the sectors formed by angle ABC. And so yesterday we looked at a proportion that had the size of the angle over 360 degrees equals the area of the sector over the area of the circle. And the one we used yesterday the most was actually dealing with circumference. And today it's going to be the same thing. We're just changing it to the area formula instead of the circumference formula. And so what is our angle here in number 4? 110. And we are trying to find the area of the sector. Now, just so you know, a sector is like this shaded region. It is a piece of the circle. The sectors we're going to be looking at go to the center of the circle. We're not going to look at a piece that's not from the center. Are you ready, Jay? I don't want to leave you behind. You ready to focus? So we put 110 degrees over 360 degrees, and that would be the area of the sector, which is what we're looking for. So I'm just going to call it X. You can use whatever variable you want. Over the area of the circle. How would I find the area of the circle? Pi times the radius squared, and in this case, the radius is 21. So pi r squared, and instead of r, I need to put 21. Now, you might say, Miss Dix, I struggle to remember the circumference formula and the area formula, which one is which. So here's how I remember which one is which. I know they both have an r, they both have a pi, and they both have a 2. It's just, does the 2 go in the front as a coefficient, or does the 2 go in the back as an exponent? And so what I remember is area is in square units. Therefore, the area formula has a square in it. So pi r squared is area. 2 pi r is circumference. Okay? So I would use my calculator, and to save time, I'm going to use this one instead of pulling out Desmos. I do 3.14 times 21 squared. And that's this number right here. And then I cross multiply that with 110 and divide that by 360. And I would get 423.115 millimeters squared. And please put the millimeters squared behind it because I want to make sure that we are aware that units are in area, they're square units. Number 5 is asking us for something different. It's asking us for the area of the circle. It's not asking us for the radius. It's not asking us for the area of the sector. It's not asking for circumference. It's the area of the whole circle. So I want you to just set up the proportion the way you think it is. You don't have to do the solving. I'll do the calculating for you. But I want to see, can you set up the proportion? What number do we always know is going to be in there? 360 degrees, because it's a circle. And can I just make a connection for you? This is very much related to percents. And you might say, how? Well, in a percent, if you want to find like the percent that something was on sale, tax, anything like that, you can also set up a proportion, and it always goes over 100 because it's 100%. And 360 is 100% of the circle, right? So it's similar to the percent proportion. 70 is our angle. Where does this 123.45 go? The top, because we're trying to find the area of the whole circle. So this area is actually the area of the gray part. How do I know that? Well, they asked me to find the area of the circle, so I know it can't be the area of the circle because that would mean they gave us the answer, right? But normally we would have some type of arrow or something drawn there just to make sure. If I give you a test on this and you're not sure, is it talking about the area of the sector or the area of the circle, you can raise your hand and ask, and I will tell you which one. Well, we just started this yesterday, so it'll be a little bit later. So 360 times 123.45 divided by 70 is 634 point, let's just do 89. Does it make sense that it's more than the area of the sector? Yeah. Yes, because it's the area of the whole thing. Any questions on how to find the area of a sector or the length of an arc using a proportion like this? Great. Let's move on to another section because I feel like this is just a repeat of circles. I do want to show you something on page 6, and you don't have to turn there if you're turning somewhere else. But on page 6, when it says area of the shaded region, if I wanted to find the area of this shaded region, what would I do? Find the area of both of them and subtract the big one minus the little one, and that would give me the shaded part. Same thing here. I'd find the area of the square, and I would subtract the area of the circle. How would I know the diameter of that circle? It's 10, because since that's the side of the square goes from one side of the circle to the other. And then here you've also got the diameter is 16. How would we find the sides of the squares on this one? Pythagorean theorem. We'd have to call these two sides x and solve for x and then find the area. Are we okay there? All right. Don't forget Pythagorean theorem. Anytime we're doing something, if you don't know what to say, yes, Pythagorean theorem. It's used a lot. All right, now page 7, today's new lesson. Now, we have finally made it to a geometry unit I have never taught. Because last year we quarantined and we were about to do this unit. We were actually in the circles unit once we quarantined. So I have never taught area of regular polygons. So hopefully I'll be able to get it across to you. But if you're like me, Sticks, you're not making sense, let me know and I will try to re-explain. Okay? I don't think we're anywhere near quarantining the whole school district again. I'm not saying you personally won't be quarantined, but I don't think we're anywhere near quarantining the whole district. So let's not. We're so close. Let's not say this. There's going to be a point where like we don't have to wear masks at all, and it'll all be gone. Eventually, I don't think coronavirus is ever going to go away, but I do think we'll eventually get to the point where we don't have to wear masks anymore. Because back in the day, when the Spanish flu came out, they had to go through this cycle of wearing masks. Like I've seen pictures where they're sitting at a baseball game outside wearing masks back when the Spanish flu was there, and it was new to the country and lots of people were dying. But what happens is, one, we do have vaccines now, and two, you do eventually start building up some immunities because you've been exposed to some things. And so I'm hoping that eventually we will be able to get rid of that. How long do you think it's going to take? I have no clue. All right. Find the area. This is my first pandemic, by the way, Austin. I know it's your first one too, but it's my first as well. I know you think I'm 100 years old, but I'm not. I'm hoping that some next school year we'll be able to go without, but more than that, I'm hoping the plexiglass can go away. I mean, I don't like masks, but this plexiglass gets on my nerves sometimes. All right, the center of a polygon is the center of its circumscribed circle. First of all, before we go any further, we need to know what this word regular means in math. Does anybody know what it means when it says a regular polygon?
It's not very common.
All great guesses. But regular means all sides are congruent. So if it's a regular pentagon, it means it has 5 sides and all 5 of them are the same length. If it is a regular hexagon, it has 6 sides and all 6 of them are the same length. Regular means all sides are congruent. And for the most part, I can't think of a case where it's not. I'm not going to say 100%, I'm going to say 99% sure. Sorry. If the sides are congruent, the angles should also be congruent. So I will look up that definition just to make sure I'm 100%, but I'm 99% sure if all sides are congruent, all the angles are also congruent. So the center of a polygon is the center of its circumscribed circle. So if you have a regular polygon, see that hexagon over here, all the sides appear to be the same length?
Yes.
It's saying the center of that polygon would be the center of the circumscribed circle. So remember, a circumscribed circle is a circle that goes through every point or vertex of the polygon. Well, you can draw a circumscribed circle around a polygon that is regular, not an irregular polygon. So the radius of a polygon is the radius of its circumscribed circle. The apothem, this is also a new word for you. The apothem of a polygon is the distance from its center to any side of the polygon. So H right here is the apothem, and they've already been nice right here and shown you that apothem is HG. So if you want to highlight that and highlight that if you like using colors. The radius would be GB. So it is not the same as the apothem because the radius goes from the center to one of the vertices, whereas the apothem goes from the center to the center of one of the sides, which means it makes a right angle. The central angle of a regular polygon is an angle formed by 2 radii drawn to consecutive vertices of the polygon. So this one, angle BGA, is what we would call a central angle. Just like when we did in the circles, it went to the center of the circle. The only difference is here that radii have to go through 2 of the vertices of the polygon. The area of a regular polygon. This is new for you guys for the most part, unless you've seen it in con. You have learned before now how to find the area of a triangle, how to find the area of a parallelogram, and even a trapezoid, even if you don't remember that formula, and a circle. But most of us have not been exposed to area of a pentagon, hexagon, octagon, any of those. So this is how you can find the area of a different size polygon, different number of sides polygon, as long as it is a regular polygon. The area of the regular n-gon with side length x is half the product of the apothem and the perimeter. So you'd say half times the length of HG right here times the perimeter of, in this case, the hexagon. Yes?
So a rectangle would be a regular polygon?
If the rectangle was a square, it would be a regular polygon.
Like a regular rectangle.
A regular rectangle would be a regular rectangle, but a rectangle that you're thinking of in your mind that's not a square would not be regular. So let's go through and try to do these problems here. In the diagram, ABCDEF is a regular hexagon inscribed in circle G. Find each angle measure. So first of all, they want us to find the angle of AGB, this piece right here. How many degrees are in the circle? 360. Well, how many of that size angles could I break this up into? 6. So how could I find the size of this angle? 360 divided by 6, which would be 60 degrees if I did the math in my head right. Yes. So 36 divided by 6 is 6. Yay, HQ says I'm right. All right, then it says AGH. So AGH is no longer the whole thing. It is this piece right here. What are your thoughts for AGH?
360 divided
Did you say half? Yes, 360 divided by 2, which is the same thing as half. So half of 60 would be 30 degrees. Measure of angle HAG. HAG. How could we find HAG? Which is this one right here.
Well, if we know that the one piece is 30, then 30 plus 30.
Right, because we know that all three make 180 degrees in a triangle. So 180 degrees minus 90 minus 60, minus 30 would give us 60. Which tells us that that triangle that this makes, BGH, that triangle, is an equilateral triangle because all three angles are 60 degrees. All right, turning, moving along. 60. All right, we're not going to do the exercise for example 1 here. I'm just going to talk you through it. How many sides does this polygon have? 9, because it's a nonagon, or you can count them. So, sorry. If you wanted to find this angle measure, how would we find like that measure of angle EJD? 360 divided by 9, and then you'd follow the same process we've already done. But let's go to example 2. A regular pentagon is inscribed in a circle with a radius of 8 units. Find the perimeter and area of the pentagon. So we have to find perimeter and area of the shaded region over here. So what do we need to find the perimeter? The side lengths of the pentagon. And once we know one side length, we could just multiply that by 5 to find the perimeter, correct? So we're going to have to use some triangle information to find the side length. So we have this triangle right here, and it is a right triangle, but we don't know two sides. We only know one side. So we can't really use the Pythagorean theorem, but we can use our friends' trig ratios. What are our trig ratios?
Yeah, let's go, friend.
We do have a special ratio we know for 30, 60, 90 triangles and 45, 45 right triangle, but we don't know if that's this yet. We could check and see. But our trig ratios are sine, cosine, and tangent. And you can use that with right triangles. So the first thing I need to do is find the measure of this angle. How would I find the measure of this angle right here? 360 divided by 5. And that gives me 72. That's not the angle of the right triangle. That's the angle of the whole piece up there. So I'd need half of it to find that angle on the top of the right triangle, correct? So half of that would be 36 degrees. So what I'm saying here is that angle GFA, this piece right here, is 36 degrees. Well, if I know an angle in a right triangle and one side length, I can find a side length using sine, cosine, or tangent, right? So I want to find GA. Is GA opposite, adjacent, or hypotenuse to the angle 36 degrees? Opposite. And 8 is given to us. Which one is that? Opposite, adjacent, or hypotenuse? Hypotenuse. So which trig ratio uses opposite and hypotenuse? Sine. So sine of 36 degrees equals x, what we're trying to find, over 8. Now, I know we have it done in the context of a pentagon, but is this sine stuff seeming like familiar? It hadn't been that long since we've done it? Okay. How do I solve for x? Multiply both sides by 8. So I'm going to use my handy-dandy calculator, and I'm going to make sure that it is in degrees and not radians, because right now it's in radians. So I put it in degrees. And I say 8 times the sine of 36. And I get 4.7, blah, blah, blah. So we're just going to say x is approximately equal to 4.7. Well, that's half of this piece over here, so I can multiply that by 2 to find out the whole thing, right? So we're going to say BA is approximately 9.4. Does everybody see that I've just found one of the side lengths of the pentagon? Well, why do we need that? Because we're trying to find the perimeter, and you can't find the perimeter without the side length. So now that I know that, to find the perimeter, I can multiply that by 5. Because aren't there 5 sides that are the same length? And I get perimeter is approximately equal to 47.02 units, because it didn't tell us inches or anything. So perimeter, this is part of our answer. Before I move on to area, does anybody have a question about perimeter? Would I have expected you to go through and figure all that out on your own the first time? No. But once I've shown this to you and gone through it a couple of times, then I expect you to say, oh, well, when I don't know the sides of a right triangle, I either use Pythagorean theorem or one of my trig ratios. So now the formula for area is 1/2 times the apothem times the perimeter. Well, we don't know the apothem yet. Which letters represent the apothem here? FG. So we got to find the length of FG before we can find the area. So let's go back to our trig ratios. In that right triangle we're looking at, FG is what in relation to 36? Opposite, adjacent, or hypotenuse? Adjacent. So which one uses adjacent and hypotenuse? Cosine. So for the apothem, we're going to say cosine of 36 degrees equals the apothem over 8. Would it be better for me to call this FG right here instead of the apothem so you'll know what we're trying to find? So I'd multiply both sides by 8 to find FG. So 8 times the cosine of 36 tells me that FG is approximately 6.47. Well, FG is the apothem. So I'd say 1/2 times 6.47 times the perimeter, which is 47.02. So 0.5 times 6.47 times 47.02. Area is approximately 152.1 square units. All right, so I'm going to give you a moment to process that and also a stretch break. So go ahead and stretch. Make sure you understand everything I just said there. I'll stop the video so it's not so long.